Jai Hind everyone, my name is Mukulit Goel. I am assistant professor in Department of MCA at AKGEC Engineering College, Ghaziabad. Today, my topic is restoring division algorithm, which is the part of the unit 2 from the subject computer organization and architecture, subject code BMC 105. Firstly, the content of my presentation, what is arithmetic division, definition of restoring division algorithm, hardware for restoring division algorithm, flow chart for restoring division algorithm, and example of restoring division algorithm. So first I will start what is arithmetic division. As we all know, we studied so many times how we do a division. For example, if we want to divide 84 by 8, if we want to divide 84 by 8, so what we do, first we convert these two terms into binary. So 8 is represented by this 1000 and 74 is represented by 1001010. So 8 will be considered as divisor and 74 will be considered by as dividend. So there is a two part, one is quotient and another is remainder. So when we divide 74 by 8, so our quotient will be 9 and the remainder will be 2. So the binary representation of 9 is 1001 and the binary representation 2 is 10. So in this presentation, we will study how this binary division will be done using adders and subtractors. So for the division of unsigned numbers, what we know the condition, if remainder is greater than divisor, use subtraction. So if it fits, what we do, we write a remainder and the remainder minus remainder n plus 1 is equal to remainder n minus divisor. What if it does not fit? We will restore the original division, and this restoration of original remainder is known as restoring division. So the restoring division algorithm is totally based on the concept of how we restore the division when it will not fit into the condition. So the restoring division algorithm is a method used to perform operations on unsigned integers in computer arithmetic. It is basically designed to efficiently compute the quotient and remainder when dividing one unsigned integer by another. So the one unsigned integer will be termed as dividend and another is termed as divisor, while also minimizing the number of computational steps. So the steps for restoring divisions are: first we initiate the process by setting up the registers. In this we use 4 registers. The first register is Q, where we restore the dividend, where we represent the dividend. Next is M, where we represents the divisor. A starts with 0, which is an accumulator. In the accumulator, the initial value is 0, and N register signifies the number of bits, and this N is also represents the number of steps for completing the division. So after initiating the process, after initiating all the values, we shift to the step 2, in which we shift the content of register of A and Q to the left. So in this restoring division, we use left shift. So in perform 3, we perform a subtraction by deducting the content of the register M from A and store the result back into A. What is A? A is the accumulator whose initial value is 0, 0, 0, 0. It depends on the number of bits. The number you are using as a divisor and dividend, how many bits it has when it is converted into a binary. So the bits in A will be decided by that. So in step 4, we examine the most significant bit of A. If it is 0, we set the least significant of Q to 1. And if the most significant is 1, we set the least significant bit of Q to 0. So what we do, if the most significant bit is 0, we convert the least significant of Q to 1, and if the most significant bit is 1, we set the least significant of Q to 0. We do just the opposite. Additionally, we restore the values of register A to its state before the subtraction with M. In step 5, we reduce the value of the counter n one by one. When we complete one step, its counter decreases. It starts with the maximum number of bits in which the accumulator must have. So in step 6, we check if the value of n has reached 0. If it does not reach the 0, we return to the step 2 and repeat the same process again and again. And finally, when we reach the process, we represents the quotient by representing the value in register Q, and the remainder will hold the values which is in the register A. So, like we see, so the quotient and remainder. The quotient is represented using register Q, and the remainder is represented using accumulators. So, this 1 0 is represented into accumulator, and this quotient is represented by the register Q. Okay. So, these are the steps for restoring division. Next, we will discuss the hardware. So, in this hardware, what we do? We have the sign bits, we have the control sequencer, we have the adder and subtractor, and we have the two values, one which is dividend, another one is divisor, one is A is accumulator. A is accumulator. So, what we use n plus 1 bit adder, which is used for the showing the number of steps. The control sequencer controls all the addition and subtraction doing for the division. So, first we have the dividend. In dividend and A, we represent it as a same. So, the number of bits in the dividend and number of bits in the A are left shifted. After doing a shift left, these will be added through a n plus 1 bit adder. So, the steps will be increased by 1. Then we do a addition or subtracting according to the steps with the divisor. This is more clear when we see a flow chart. So, now we are moving to the flow chart of restoring division. So, in flow chart, what we do? We define the n number of bits in the dividend. A is equal to 0, M is equal to divisor, and Q is equal to dividend. So, in the first step, as we say, what we do? We do a left shift of AQ. Okay. So, first we shift the content of A and Q 1 bit to the left. Then we do a subtraction. A is equal to A minus M. This A is equal to A minus M will also be represented as A is equal to A plus minus M. Okay. And this minus M will comes by the 2's complement of values of M. So, if you don't want to do subtraction and you want to do simply addition, then you can do it through A plus minus M, and minus M is the 2's complement of the values of M. After this, we check what is the most significant bit of A. If it is 0, we convert the value of Q0 to 1, and it is 1, then we convert the value of Q0 to 0, and we restore the value of A before this subtraction. Then we decrement the counter n is equal to n minus 1, and if n is equal to 0, then we find the quotient and the remainder, and if this n is not equal to 0, then we repeat the steps from the steps before the left shift of A and Q. This is become more clear when we understand with the help of example. So, in this presentation, I will show you around 2 and 3 examples. So, I will start with the example 1, in which what we are doing, we are doing 11 divided by 3. Okay. So, we are dividing the 11 by 3. So, the value of M is equal to 00011. Q is equal to 1011. So, the value of what is the binary value of 3 is Binary value of 3 is 011. So for making it 5-bit, we add 3 zeros to the left. And what is the binary value of 11 is 1011. So we take the value of the quotient. Oh, sorry, we take the value of the dividend. So n is equal to 4. So what we start, first we initialize, then what we have done the shift left of AQ. So as you can see, we shift one bit of Q and A to the left. So the value is 1011. So we shift 1011 to 10110. So our Q become 110. And what is the value of A? It is our Q, and the value of A is 00001. From where this one comes, this one is this. This one is left shifted. All three we have left shifted, and one will come here. After this, we do a subtraction of A is equal to A minus M. Means what we have done? We have minus 00001 minus 00011. After the subtraction, its value become 11110. What we do now, as per the flow chart, what we check what is the most significant bit of A. So in this example, the most significant bit of A in the first step is 1. So what we do, we update the value of Q0. We update the value of Q0 with 0. We update the value of Q0 with 0 and restore the value of A. So what we do, we update the value of Q0 with 0, and what we have done, we also restored the value of A, which is before the subtraction. So the value before the subtraction is 00001. So we restore it to here. So it is the completion of our one step. In next step, again we do a shift. So we shift a one bit left. So this 0 comes here, this one here, and this 0 goes there, and this one shift one bit left, and other three are remaining zeros. Again what we do a subtraction. So we subtract 00010 with 00011, and the output will be 5 ones. Again what we have seen, the most significant bit of A is 1. So again what we will do, we put the value of 0 in place of Q0 and restore the value of Q before the subtraction. This is the completion of our third step. After the completion of third step, what we do? Again we do a left shift, 0, 0, 1, 1, 1, 0, 1. After this shifting of left, again we do a subtraction, and after the subtraction its value becomes 00010, and you see here that the most significant bit of A is 0. So when the most significant bit of A becomes 0, what we'll do? We update the value of Q0 to 1. So what we have done? We update the value of Q0 to 1. Here you can see. Here you can see that we update the value of Q0 to 1. Okay, and in this case we have not restored the value of A to the previous state before the subtraction. What we'll do? We have updated the value of A. Okay. This is the completion of second step, and now again we do a division. After doing a for division, we are doing the left shifting. After doing the left shifting, we do a subtraction. After doing a subtraction, here comes 0, 0, 0, 0 and Q0 is equal to 1. But what we have seen कि now our subtraction is, now our division is complete. Our n becomes 0. So what we have do? We have taken the value of Q and A. Q is equal to and Q is equal to and A is equal to and A is equal to. So the Q is equal to 0, 0, 1, 1. A is equal to 0, 0, 1, 0. So if we now do a division, normal division, what we find, 3 3s are 9 and it becomes 2. Okay. So the remainder is 2 and the quotient is 3. So the Q represents the value of 0, 0, 1, 1, which represents 3 in decimal, and A represent is 0, 0, 1, 0, which represents 2 in decimal. Okay. Okay. So with this, so with this, what we have do? We have find the division which is 11 by 3 using the division restoring algorithm. Again, I will want to explain through an example, another example in which what we are doing dividing 7 by 6. We are dividing 7 by 6. So same we are taking m is equal to 110, which represents 6. Q is equal to 111, which represents 7. To making it a 4-bit, we add 1 bit 10 to the left of the m, and now we start our division. So first we initialize the values. So first initialization of A is 0, 0, 0, 0, m is 0, 1, 1, 0 and Q is 1, 1, 1. First step, what we do? We do a left shifting. So if while doing the left shifting, we shift one bit of the values of 1. After this, we do a subtraction of 0, 0, 0, 1 by 0, 1, 1, 0. 0, 0, 0, 1 by 0, 1, 1, 0. This becomes 1, 1, 0, 1 by binary subtraction. So what we see a most significant bit of A, which is 1. So we convert the least significant of Q to 0 and restores the value before the subtraction. Now we comes to the second step, which is 0, 0, 1, 1. Now what we do? We do a left shift. So 0, 1, 1, 1 and 0 and 0. Okay. Again we do a subtraction, then it comes 1, 1, 1, 1. The most significant bit is 1. So we put the least significant 0 and restore the value of Q to the previous state. Then we do a subtraction, the value comes 0. We update the value of most significant to 1, and so this is the final value, because in 4 bits we do with it 3 steps. So while doing it with 3 steps, so our Q remains 1 and our A is also remains 1. So you can see when we do 7 divided by 6, 7, 1, 6, 1. So 1 is the remainder and 1 is the quotient. So it is the quotient and it is the remainder, which is the same represented by the values of Q and R, which is 1 and 1. Okay. Now we come to the example 3 with the same, which we are doing the same division, which is 13 divided by 4. Same initialization we do. I am again taking this third example to make the concept more clear ki how we are doing this division. So same we are applying the value of Q, which is the representation of 13, which is 1101. M is equal to 0100. For making it 5-bit, we are applying left 0 at the left bit, and A is the initially we have the value 0. We start with n is equal to 4. First we initialize, then we do the same left shift 1 bit left between the A and Q. In the division, what we have to take care of, that we don't have to shift the values of M. The value will of M will remain the same in each step. What we only do this, we are whatever calculation we are doing, whatever addition and subtraction we are doing, we have to do only in A and Q. We no need to touch the value of M. Okay. So first we do a left shift, then we do a subtraction. After subtraction, what comes? 1101. So the most significant bit of A is 1. So we convert the most significant bit of Q to 0 and restore the value before the subtraction. Again, we do a left shift. After doing a left shift, we do a subtraction. In subtraction, we got the values of 11111. After checking this, the most significant bit of A is 1, and then we convert the least significant bit of Q to 0 and we restore the value before the subtraction. In the same way we do, and after doing the 4 steps, our answer will come in terms of 1 and 11. What we see, if we divide 13 by 4, it's 3, 12, 1. So the value of A represents our remainder, which is 00001, which is equal to 1 in decimal. Our value of Q will represent the quotient, which is 0011, is equal to 3 when we convert it into binary, sorry, in decimal. Okay. So in this way we have do a division of any unsigned integer using restoring division. After this example, I just want to tell you the one disadvantage of this restoring division. The disadvantage of this restoring division is this: by restoring the values of A, what we are doing, we are making it complex, or we can say it will slow down the process of division. So there is another way of division which we call it as a non-restoring division, in which there is a different flow chart, it has a different hardware implementation, but it is faster than restoring division. So if in future I will get any chance, I will also define the non-restoring division and compare it with restoring division algorithm. Okay. So with these examples, I think it is clear to all that what is the restoring division, what steps we do, and what we store in the values of register which is used for the division. And the values of this division come same as we do it in a binary, or we do it in our basics when we are in the school time. With this, my lecture is complete. Thank you very much.